In this lecture, I'm going to talk about the dot product. So, the dot product is a bit like multiplication almost. What you have to do is you have two vectors and you want to see how their forces interact. That's kind of what you're getting with the dot product. Yeah. It almost is a way of mapping two vectors upon each other. So the general formula for dot product, given any vector v and any vector u, the dot product of u dot v is v1 u1. So you multiply each of the elements by each other. But what you end up here with is a number, not a vector, a number. So important to remember that again and again and again. So you do a dot product of something. So if you do a dot product, for example, of a vector by itself, you get the magnitude squared. What you have here is you do the dot product of the vector, you look at how it projects onto each other. Now, simple dot products. V is 3, 4, u is 5, 6. So now we have u dot v is equal to 3.5, or 3 times 5, 4 times 6. Add them together, and you end up with a number. Just keep that in mind, a number, a number, a number. V dot v, dot product of itself, is 3 times 3 plus 4 times 4 is 25. The norm of our vector v is equal to 5, or square root 25. That's just dot product squared, square root of dot product. And u dot u is 5.5 plus 6.6, 6 times 6, 61. So here we have the generalized formula for 2D. For 3D, same premise, u dot v, 1 times 2, 2 times 3, 2 times 6. Gives you 15, yeah? V dot v is just you multiply 1 by itself, 2 by itself, 3 by itself, yeah? Same with v dot v, yeah? Dot product, once again, is a number, not a vector, a number. As I said, u dot v is the length squared. Now, there's an interesting thing is that if two vectors are truly perpendicular at right angles, then the dot product is 0. This is a very important rule because what you're doing is you're projecting u onto v. If there's nowhere to project on, the answer has to be 0. So if you expect the dot product to be very small if the angle between two are very large, yeah? Now, u dot v, v dot u, it's commutative, like multiplication. 3 times 4 is the same as 4 times 3, yeah? It is also distributive, just like multiplication. 3 times 4 plus 2, that's 3 times 4, which is 12, plus 3 times 2, which is 6, is the same as 3 times 6, which is 18, yeah? And it's associative, that's just for scalar product. But it observes these are the rules. These are important rules because you might worry, oh, I'm doing it this way or that way. It should give you the same answer. It will give you the same answer, I mean. What dot product can also do is get the angle between two vectors. So this is our original formula for the dot product. We have the formula where we calculate it. It's u1, v1.u1 plus v2 times 2. But this is actually the underlying formula. So what it says is, if you know the dot product is two vectors, and you find out the length of the vector, of each vector, then you can find out the angle. So you rearrange the equation such that v dot u divided by the length of each is equal to the cos of the angle. So once again, you have some vector like this, and this works for n dimensions. Does not matter what dimension the vectors are, it'll give you that angle. So now we have a few bits of information that isn't relevant for the dot product. If you know that the dot product of two things that are perpendicular is 0, then you can think about the basis vectors, because the basis vectors They don't have to be, but it's nicer if the basis vectors are perpendicular. A basis vector is something that describes a whole space. So the ones we all classically think of are x, y, and z, or z, x, y, whichever way you want to draw it. There are classic basis vectors. They're linearly independent. Every point can be rewritten in the form of x, y, and z. So in 2D, we have our y direction, and we have our x direction. And what that in vector form is I, and that's j. And so every single point can be referred to in terms of i's and j's. So every single coordinate can be rewritten. And the reason why I do that is it's easier to do calculations when it's in the ij format. Because little things like this is, what's the dot product for I dot j? So I is not 1, j I is 1 naught, j is not 1. So the dot product of that is 1 times 0 plus 0 times 1, which equals to 0. Now, I said this before, they're perpendicular, so dot product is 0. They don't have to be, but it's nice. Same thing for 3 dimensions. We have I, j, and k. And so the k is now the z, and that's just 1, 0, 0, 0, 1, 0, 0, 0, 1. Yeah? And we can just rewrite, once again, it's easier to work in vector format if you're doing additions and multiplications in higher dimensions, thinking about I, j, k. And what we have here is I dot j is equal to j dot k is equal to I, j. And they're always 0 because I, j, and k are each perpendicular to each other. So therefore, the dot product will always be 0. So that brings us to the end of the dot product. The dot product is going to turn up later when we look at the divergence of a flow field. It's not just for simple vector stuff. It actually has very important meaning for when we're talking about actually how fluid flows or things move in the world. So the next lecture, we'll talk about the cross product.